Yo, hello everybody. Welcome back to the stream. Okay. All right. We'll let some people roll up in here. How about you? Let's give it a second. Alrighty. All right. We're live on Twitch too. Airbnb Wi-Fi is pretty good. All right, let's go ahead and get started. Why not? You know, got to get into it sooner rather than later, yeah? Okay, let's go ahead and start. Let me know if you'd like me to turn up my volume. I think I might turn up my mic to, I usually do it to 3 dB. That kind of helps compensate for my mumbling. Okay, turned it up. All right. I think we're okay. Let's go ahead and get started. All right. Hello, everybody. Welcome back in. Hope you're having a wonderful day so far. My name is Michael, and welcome back to the channel. Today, we're going to be jumping back into C Programming: A Modern Approach, 2nd edition by K.N. King. We're going to be jumping into and starting and completing the reading of chapter 11. Chapter 11, Pointers. I'm actually really excited to get into this chapter. I feel like this will tie a lot of loose ends together regarding C and some of its, entry-level syntax and how to kind of manage the actual memory behind the code. Oh boy. Let's go ahead and get started here. I'm recording, so we are live. This is the full, this is a chopped up version for my live stream where we read this book and do the problems at the end of the chapters live on stream in its entirety. If you'd like to join me, consider joining me usually around 7 p.m. PST as I stream after my 9-to-5 job. Learning and teaching myself computer science and building programs, projects from scratch. And having fun. All right, that's enough of the intro. I will say there's a Discord link down below where you can get access to all of my notes and other resources for how I have taught myself so far. So if you are interested in joining along and providing feedback and whatnot, consider joining. Thanks. Okay, that's enough of that. That's cringe. Okay, let's go ahead and get started here. Welcome in, everybody. Again, this is the live stream for Chapter 11 Pointers here. I'm going to be chopping it up for the full audiobook read-along if you would like to listen to that, whether you're commuting to work or whatnot. I think it's a great opportunity to listen to it and get a second exposure or first exposure if you're following along. So without further ado, let's go ahead and get started. Chapter 11, Pointers. The 11th commandment was thou shalt compute, or thou shalt not compute. I forget which. Pointers are one of C's most important and most often misunderstood features. Because of their importance, we'll devote 3 chapters to pointers. In this chapter, we'll concentrate on the basics. Chapter 12 and 17 cover more advanced uses of pointers. We'll start with the discussion of memory addresses and their relationship to pointer variables. Section 11.1. Section 11.2 then introduces the address and indirection operators. Section 11.3 covers pointer assignment. Section 11.4 explains how to pass pointers to functions, while sections 11.5 discusses returning pointers from functions. 11.1, pointer variables. All right, let's go ahead and get some notes going here. Cool. The first step in understanding pointers is visualizing what they represent at the machine level. In most modern computers, main memory is divided into bytes, with each byte capable of storing 8 bits of information. Right? We know this. Each byte has a unique address to distinguish it from the other bytes in memory. If there are n bytes in memory, we can think of addresses as numbers that range from 0 to n-1. See the figure at the top of the next page. An executable program consists of both code, machine instruction corresponding to statements in the original C program, and data, variables in the original program. Each variable in the program occupies 1 or more bytes of memory. The address of the first byte is said to be the address of the variable. In the following figure, the variable I occupies the bytes at addresses 2000 and 2001, so I's address is 2000. N-1, an executable program consists of both code, machine instruction, corresponding statements in the program, and data. Variables in the original. Each variable in the program occupies 1 or more bytes of memory, depending on the type of variable. Right? We know that. The address of the first byte is said to be the address of the variable. Got you. So wherever I first lands on is the address of the I variable as it extends to multiple bytes. Okay. Let's take some notes here. I want this go to hold on, guys. My girlfriend's calling me. All right, we're good. Sorry about that. Okay, let's go ahead and keep going. So let's get some notes here. So we'll say main memory is divided into bytes. Does this have... Oh. Well, it's got some new syntax highlighting here, I guess. We know with each byte capable of storing 8 bits of information. Each byte has a unique memory address. A little bit. Each byte has a unique memory address to distinguish it from other bytes in memory. If there are n bytes in memory, great, cool. An executable program consists of both machine code, blah, blah, blah. Each variable is in the corresponding. So, right, we'll say variables core can occupy one or more bytes in memory depending on type. The address of a variable is the first the address of the variable is the address of the first byte the variable occupies. Right. So we say we'll copy out this guy here. Okay. So we'll say address byte with each byte capable of storing 8 bits of information. Okay, cool. Let's keep pushing. Here's where pointers come in. Although addresses are represented by numbers, their range of values may differ from that of integers, so we can't necessarily store them in ordinary integer variables. We can, however, store them in special pointer variables. When we store the addresses of a variable I in the pointer variable p, we see that p points to I. In other words, a pointer is nothing more than an address, and a pointer variable is just a variable that can store an address. Instead of showing addresses as numbers in our example, I'll use a simpler notation. To indicate that a pointer variable p stores the address of a variable I, I'll show the contents of p as an arrow directed towards I. Okay, so then we have pointer variables, which are special variables, or just say variables specific variables used to house variable addresses of specific variables used to house pointer addresses of other variable types. Something like that. What's up, Cav? How's it going, man? First commenter. Thanks for coming in, dude. Let me go ahead and actually, I think I might remove the chat while I'm doing this kind of reading here. When we store the address of variable I that points to variable P, we say that P points to I. That's right. So then we say, kind of take this example here, put that there. Okay. Declaring pointer variables. A pointer variable is declared in much the same way as an ordinary variable. The only difference is that the name of a pointer variable must be preceded by an asterisk. Int star P. This declaration states that P is a pointer variable capable of pointing to objects of type int. I'm using the term object instead of variable since, as we'll see in chapter 17, P might point to an area of memory that doesn't belong to a variable. Be aware that object will have a different meaning when we discuss program design in chapter 19. Something like that. So then we'll do a little declaring. It's going to be like int star P, right? P is a pointer variable capable of pointing to objects of int. Okay. Pointer variables can appear in declarations along with other variables. Int I, j, an array of size 10, array b of size 20, a pointer p, and a pointer q. In this example, I and j are ordinary integer variables, a and b are arrays of integers, and p and q are pointers to integer objects. C requires that every pointer variable point only to objects of a particular type, the referenced type. So int star p points only to integers. Double star q points only to doubles, and char star r points only to characters. There are no restrictions on what the reference type may be. In fact, a pointer variable can even point to another pointer. So then you can say, we'll kind of do like, can appear in declarations with other of the same type. int I j ray 10 b 20 star p star q. Right. So we'll say a reference type. Right, something like that. And then I will take a screenshot of this little thing here and put that in the notes. So this one is going to go up here. Okay. Nice. How's it going? I appreciate you hacking up. What's going on? I know it's not a bot. I'm here. What's going on, Dr. Plummer? John. Appreciate you coming in. Okay. Oops, spelled that wrong. Declaring. Okay, cool. Nice. That was 11.1. 11.2. Oh, the address and indirection operators. And this is 11.1, pointer variables. Okay, let's keep going. Hey Ahmed, how's it going? Appreciate you for coming in. Yeah, C is still heavily used. I wanted to dive deeper, understand what was going on in my Python, maybe write my own packages for Python in C, and get better at programming with computers in general. So, and Professor David Malin still recommends having a pretty good understanding of C, and I think he's a pretty smart dude. I saw that in a recent interview of him lately, so okay, let's go. 11.2, the address and indirection operators. C provides a pair of operators designed specifically for use with pointers. To find the address of a variable, we'll use the ampersand, or address operator. If x is a variable, then ampersand x is the address of x in memory. To gain access to the object that a pointer points to, we use the star, or the indirection operator. If p is a pointer, then star p represents the object to which p currently points to. So if you have a variable that's an integer, let's say 10, right? Ampersand of that variable would return you the address of where that integer 10 is located in memory. Whereas if the other way around, you have an address for an integer, and it happens to have the value of 10 at that point.
You're not that guy, pal. Trust me. You're not that guy.
I need to...
Okay? You? Absolutely.
The stream alerts... I forgot how to pretend to mute them in... If I hide them, but... Yeah, that's whatever. Thanks for the sub, dude. Appreciate you. You're awesome. Okay, sorry. It just kind of throws us off. Okay, it's hard to edit out in the recording. Okay, so then if you have the other way around, where you have an address that happens to point to an integer, which happens to have a value of 10 at that memory location, the bytes make up the value of 10 for that integer, then to do star p would return you back that value of 10 of that address p, right? Okay, that makes sense. I like that. So let's do the address operator. So which is going to be, so we'll say to find the address of a variable, we use the ampersand. It's 7. The address operator. If x is a variable, so we'll say if, I know this is in the note, it's like in the book, but I want to, typing it out and going through it really helps to solidify it. And it's kind of like a good spark note for other people. If x is a variable, then ampersand x is the address of x in memory. Cool. So now we have the indirection operator, right? So then we say to gain access to the object that a pointer points to, we use the star, which is the indirection operator, right? And then we say if p is a pointer, then star p represents the object to which p currently points to. Cool. Nice. Let's keep going. Bro. Ahmed comes in here and starts giving out advice. First time he's ever been in the stream. For what we should learn. Says we should learn Python. Bro. Rage baiting me. Rage baiting me so hard. The address operator. Declaring a pointer variable sets aside space for a pointer, but doesn't make it point to an, what the heck, sorry. The address operator. Declaring a pointer variable sets aside space for a pointer, but doesn't make it point to an object. Int star p points nowhere in particular. It's crucial to initialize p before we use it. One way to initialize a pointer variable is to assign it the address of some variable, or more generally, L value, using the ampersand operator. So we have int I, which is an integer, normal integer type, and we have an int star p, which is a pointer to an integer. We can say p is equal to the ampersand I, which is the address of I. By assigning the address of I to the variable p, this statement makes p point to I. It's also possible to initialize a pointer variable at the time we declare it. Int I, int star p equals to ampersand I. We can even combine the declaration of I with the declaration of p, provided that I is declared first, where int I, comma, star p equals to ampersand of I. The indirection, okay. So we'll say declaring sets aside space for a pointer but does not make it point to an object. For example, int star p this points nowhere in particular. Right? It's just it's just like initialized. It's not, declared on something or defined against something, right? As something. It's just initialized. It's crucial to initialize p before we use it, or not initialize, I guess. It's declared. We're declaring, we haven't defined or initialized it. It's probably the better word to use. So one way to initialize a pointer variable is to assign it the address to some variable. So we'll say assign the pointer variable the address of some variable to initialize. Initialize it for use. Can be used as an L value when combined with the ampersand address operator. Right, and so we can do this here. Copy image. Come on. Paste. That's my and be not working. My keyboard just die? Oh, it might have. Ain't no way. What just happened? 57%. There we go, we're back. Okay. No, my keyboard didn't die. Still good. Put back in my phone. Okay. Cool. Nice. Okay. All right, let's move on here. Um, Yeah, it just creates a pointer variable on the stack, like John said, yeah. Well, all their suggestions is so funny. Everybody's an expert. Okay. Um, the indirection operator. Once a pointer variable points to an object, we can use the indirection operator, asterisk, to assign to access what's stored in the object. If p points to I, for example, let me restart that. Once a pointer variable points to an object, we can use the asterisk indirection operator to access what is stored in the object. If p points to I, for example, we can print the value of I by calling printf for %d, which is an integer, \n, and insert into that %d asterisk p. Printf will display the value of I, not the address of I, right? Because I, or p, points to I, so we can call star p to extract the value at the address of p, which is the integer I. That's a mouthful. The mathematically inclined reader may wish to think of the indirection asterisk as the inverse of the address operator. Applying address to a variable produces a pointer to the variable. Applying star to the pointer takes us back to the original variable. J is equal to star address I is equal to the same as j is equal to I, right? Where we have some variable I, we get the address of the variable I. We then extract from that address the value of I, so it's just the same thing as j is equal to I. As long as p points to I, star p is an alias for I. Not only does star p have the same value as I, but changing the value of star p also changes the value of I, right? Because it's pointing to the same memory address of that variable I. Star p is an L value, so assignment to it is legal. The following example illustrates the equivalence of star p and I. Diagrams show the values of p and I at various points in the computation. P equals to the ampersand I. Right, so in this line here, p is just equal to the address of the variable I. So p in this instance points to I. I is equal to 1, so p points to, is still the address of I, which points to the value of 1. So if you print I here, it prints 1, and if you print star p here, which is the, indirection of p, or the kind of unpacking, whatever, for lack of a better term, and then we can assign actually star p to equal 2, which will make the variable I actually equal to, right? They're aliases, star p and I. We can printf I, which is now 2, and printf star p, which is 2 as well. That's a cool point. So let's do that, make that little note here. So as long as p points to I, star p is an alias for I, right? Not only does star p have the same value as I, but changing the value of star p also changes the value of I. And then we can say, in this kind of subnote here, that star p is an L value so assignment to it is legal. So then I'm going to actually take this example here, which is really nice. We'll put this in our notes to reference. Beautiful. Okay. Warning. Never apply the indirection operator to a non Warning. Never apply the indirection operator to an uninitialized pointer variable. If a pointer p hasn't been initialized, attempting to use the value of p in a way causes undefined behavior. In the following example, the call of printf may print garbage, causing the program to crash, or have some other effect. Int star p, printf for the insertion of an integer, and insert star p in there is wrong. Int star p actually doesn't point to anything. It's just declared. Assigning a value to star p is particularly dangerous. If p happens to contain a valid memory address, the following assignment will attempt to modify the data stored at that address. So we have int star p equals to 1. If the location modified by this assignment belongs to the program, it may behave erratically. If it belongs to the operating system, the program will likely crash. Your compiler may issue a warning that p is uninitialized, so pay close attention to any warning messages you get. So it's saying, because of that alias behavior, I'm guessing this is maybe dangerous to do. Assigning a value to star p is particularly dangerous. If p happens to contain a valid memory address, right? Like in that last example, right? If you did star p and override 2, you actually have side effect of overriding I as well. And what if I is used in a different part of the program and needs, it's interesting. So would there be cases where this wouldn't be wrong, like to be like in specific use cases? That's my question. Okay. I'm going to ask that. I'm going to take this. I'm going to say, let's open up the chat. I have a question on this. I am interested in learning more. My guess is that by blindly modifying the alias to a variable through a indirection of a memory or pointer variable, we may not be accounting for the use of the other end, the alias on the other end somewhere else in the program. Is this a correct interpretation? Let's discuss this more. You're circling the topic, but the danger the book is describing is even more fundamental than aliasing. Slow it down. You're reading computer system. No, we're not reading this one. Declares the variable pointer, but it doesn't initialize it. Oh, okay, so it doesn't actually initialize it, right? We just declared this variable pointer, and we're trying to assign some garbage memory address. Or no, it's not garbage. It has an address, but it's to some garbage value, right? It has an address of size int, of for size. Let's keep reading. So P contains whatever random bits happen to be in that memory location. Yeah, so we initialize some memory here through star P, right, to point to an integer type. And so it's just pointing to some random integer in memory to start until we assign it to something. Right, yeah. The program never set that. So star P equals to 1. Now the program says go to that memory address stored inside P and write 1 there. But we never decided what address P should hold. So this particular address could be important, but why would, here's my question is why would the compiler assign to the uninit star P pointer variable an important system variable? Would there not be protections, or is it just random for an integer? But for whatever type size is being declared. But the compiler's not assigning P to an important system variable. It's not assigning anything at all. P simply contains whatever bits were already sitting in that memory location. Now, why is it saying that those bits might be potentially important if they're just garbage? P simply contains whatever bits. Let's unpack that. What actually happens when you declare a pointer? In star P, this is a local variable. It lives on the stack. The compiler typically generates something like allocate 8 bytes on the stack for this P. That's it. It does not clear the memory. Clearing memory would cost CPU cycles and C unintentionally avoids hidden overhead. So it's just some random left behind integer. Now, why couldn't we just override that random value? So if P randomly points to this, you might still have valid memory belonging to your process. That still might be valid memory belonging to your process. Why would it choose a memory address to declare on that may belong to our process? The key correction, it didn't choose that address. Nothing is choosing an address for P. The address is simply whatever bits already exist in the stack slot where P lives. Your program gets a virtual address space. When your program starts, the operating system gives your process its own virtual memory layout. Like this. Oh, I only did like 3 questions. Are you serious? High address, stack, heap, and then low address. All this memory belongs to your process only. Your program can read, write almost anywhere inside of it. When you write $P, the compiler usually places P on the stack. So the stack frame might look like this. The CPU simply reserves 8 bytes for P. Those bytes already contain old data from earlier stack usage. So it can't get a location randomly, I guess, that is already in use. It's truly garbage until we set it. The key point is a pointer variable itself is a chunk of memory on the stack, wherever you declare it. The memory already contains whatever bits were there before garbage. The pointer doesn't magically pick a valid free memory location for you. Whatever value happens to be in that memory might look like a valid address, often inside your process, because stack memory gets reused until you initialize it with null, the address of a memory variable, or memory from malloc. It's just indeterminate garbage. So like if we had int I equals to 10 and $P would not randomly, I don't know why I keep using this, happen to start at the address of I. Exactly. It's extremely unlikely that an uninitialized pointer will just happen to point at a nearby variable like I. I lives somewhere on the stack. P also lives somewhere on the stack in its own slot. The contents of P are whatever bits were already in P stack memory, not related to I. My question, though, is, I guess it's maybe deeper than that, is I protected from pointer declaration while still in use? Yes, I itself is protected in the sense that the storage location is fixed and valid for the duration of its scope. I is a fixed memory address on the stack. As long as you're inside that block, its scope, I ampersand I is still valid. Well, yeah, that's kind of not what I was asking. Like, because I happens to be on the stack, like, what is the chances that $P happens to also hit that stack address just out of some slim odd? Now, is that stack address protected as long as this is still in use? That's my question. It's dangerous because if P doesn't contain a valid address, you will be attempting to read invalid memory. It usually causes a crash. That's why they suggest always initialize variable. And start P is like saying go to the address stored in P, but if P contains garbage, data will crash. Okay. That's enough deep diving there. Let's keep pushing. Okay. Let's keep going here. That was a little bit of a long detour, sorry. Probably could have been done with the chapter by now. Oh boy. This is good though. I'm learning a lot about pointers that I didn't know before. Okay, 11.3, pointer assignment. C allows the use of assignment operators to copy pointers, provided that they have the same type. Suppose that I, j, p, and q have been declared as follows. Int ij star p star q. The statement p equals to the address of I is an example of pointer assignment. The address of I is being copied into p. Here's another example of pointer assignment, where q is equal to p. This statement copies the contents of p, the address of I, into q, in effect making q point to the same place as p, which is I. Both p and q now point to I, so we can change I by assigning a new value to either star p or star q. Yep. A number of pointer variables may point to the same object. Be careful not to confuse q equal with p with star q equal to star p. The first statement is a pointer assignment. The second isn't, as the following example shows, where p is equal to the address of I and q is equal to the address of j. I is equal to 1, so p is pointing to an integer 1. Q is just pointing to the address of j, which doesn't have any assignment yet. If we say that star p is equal to, or if we say that star q is equal to star p, then this unpacks the value of p, which is 1, and assigns 1 to star q, which is j. So we override j with the value at star p, which isn't an alias, they're both distinguished. The assignment star q equals star p copies the values that p points to, the value of I, into the object that q points to, the variable j. Exactly. I'm going to kind of just take this example here, I think, for this section. Let me, over here. Like this. Okay. And that'll be it for that section. Quick section. 11.4, pointers as arguments. Okay. 11.4, pointers as arguments. So far, we've managed to avoid a rather important question. What are pointers good for? There's no single answer to that question since pointers have several distinct uses in C. In this section, we'll see how a pointer to a variable can be useful as a function argument. We'll discover other uses for pointers in section 11.5 and in chapters 12 and 17. We saw in section 9.3 that a variable supplied as an argument in a function call is protected against change because C passes arguments by value. This property of C can be a nuisance if we want the function to be able to modify the variable. In section 9.3, we tried and failed to write a decompose function that could modify 2 of its arguments. Pointers offer a solution to this problem. Instead of passing a variable x as the argument to a function, we'll supply ampersand x, a pointer to x. We'll declare the corresponding parameter p to be a pointer. When the function is called, p will have the value of the address of x, hence star p, the object that p points to, will be an alias for x. Each appearance of star p in the body of the function will be an indirect reference to actual x, allowing the function both to read x and to modify it. To see the technique in action, let's modify the decompose function by declaring the parameters int part and fract part to be pointers. The definition of decompose will now look like this, where void function decompose takes in a double x, a long pointer for int part, and a double pointer for frac part. So we say we cast x to a long, and we set that equal to you take this in as a parameter. Oh, so that we can have it globally, right? So the address int part gets saved as long cast to x. So it'll get rid of the fractional part or the decimals. And then we say the value frac part pointer is equal to x minus the value at int part. The prototype for decompose could either be void decompose double x, comma long star int part, comma double star frac part, or void decompose double, comma long star, comma double star. We'll call decompose in the following way, where we decompose pi and we have ampersand I and ampersand D. So we have to give addresses, right, which are pointers. Because of the ampersand operator in front of I and D, the arguments to decompose are pointers to I and D, not the values of I and D. When decompose is called, the value 3.14159 is copied into X, a pointer to I is stored in int part, and a pointer to D is stored in frac part. So we have 3.14, which is X. Int part points to a variable I, and frac part points to a variable D. The first assignment in the body of decompose converts the value of x to type long and stores it in the object pointed to by int part. Since int part points to I, the assignment puts the value 3 into I. So 3.14 gets cast to long, dropping the float or the kind of decimal value and leaving the 3 saved in I. The second assignment fetches the value that int part points to, the value of I, which is 3. This value is converted to type double and subtracted from x given 0.14159, which is then stored in the object frac part points to. Right, we get the fractional part there into D. When decompose returns, I and D will have the values 3 and 0.14159, just as we originally wanted. Using pointers as arguments to functions is actually nothing new. We've been doing it to calls of scanf since chapter 2. Consider the following example where we have int I and we call scanf quote %d quote comma the address I. we must put the address operator in front of I so that scanf is given a pointer to I. That pointer tells scanf where to put the value that it reads. Without the ampersand, scanf would be supplied the value of I. Although scanf's arguments must be pointers, it's not always true that every argument needs to be the ampersand operator. In the following example, scanf has passed a pointer variable. We have pointer star p is equal to the address at I. We can directly just put in p, right? Because p is a pointer. Since p contains the address of I, scanf will read an integer and store it in I. Using the ampersand operator in the call could be wrong. Using the address operator in the call would be wrong. Right, p is already an address. You can't get an address of an address. Scanf would read an integer and store it in p instead of I. So it actually would store it in p instead of I. Failing to pass a pointer to a function when one is expected can have disastrous results. Suppose that we call decompose without the ampersand operator in front of the I and d with this. Decompose expecting pointers as its second and third arguments, but it's been passed the values of I and d instead. Decompose has no way to tell the difference, so it will use the values of I and d as though they were pointers. When decompose stores the values in star int part and star frac part, it will attempt to change unknown memory locations instead of modifying I and d. If we provided a prototype for decompose, as we always should do, of course, the compiler will let us know that we're attempting to pass arguments of the wrong type. In the case of scanf, however, failing to pass pointers often goes undetected by the compiler, making scanf an especially error-prone function. So we have an example program here, finding the largest and smallest elements in an array. To illustrate how pointers are passed to functions, let's look at a function named max_min that finds the largest and smallest elements in an array. When we call max_min, we'll pass its pointers to two variables. Max_min will then store its answers in these variables. Max_min has the following prototype. Max_min is a void function that takes in an integer array, an int n, a pointer max, and an integer pointer min. We call max_min. A call of max_min might have the following appearance. Max_min b, capital N, ampersand big, ampersand small. B is an array of integers. Capital N is the number of elements in B. Big and small are ordinary integers variables. Big and small are ordinary integer variables. When max_min finds the largest element in B, it stores the value in big by assigning it to star max. Since max points to big, an assignment to star max will modify the value of big. Max_min stores the smallest element of B in a small. Max_min stores the smallest element of B in small by assigning it to the star min pointer. To test max_min, we'll write a program that reads 10 numbers into an array, passes the array to max_min, and prints the results. Enter 10 numbers. Largest is 102, the smallest is 7. Here's the complete program. We include the standard I/O. We define capital N to be 10. We have our function prototype and our main function, which has an integer array B of size big N, integer I, big and small. Printf prints enter 10 numbers. we're going to loop over 10 times and scan those numbers into the values of array address at index of I. Max underscore min is defined where we print largest and smallest and we return 0 given big and small. So given the address of big and the address of small. Oh no, we call max min given the address of big and the address of small, and then we print largest and smallest for big and small. Now here is where we define max min. We have int I. We say that pointer max and pointer min equal to the first value in the array. We go from value 1 in the array, not 0, because we've already evaluated that. Well, 1 forward. If the value that we're currently evaluating is greater than the value at the pointer max, then pointer max is equal to that value. Else if array that else if the value we're evaluating is less than the value at the pointer min, we're going to set pointer min value to equal that array index I that we're evaluating on. Okay. The notes are getting a little bit rocky here. It's all right. Notes are getting a little bit rocky, but it's kind of a lot of information, a lot of examples. (11.5) Pointers as return values. We can not only pass pointers to functions, but also write functions that return pointers. Such functions are relatively common. We'll encounter several in Chapter 13. The following function, when given pointers to two integers, returns a pointer to which integer is larger. Int star max has parameter of a pointer to an integer a and an integer pointer b. If the value at the pointer a is greater than the value at pointer b, return a, which is a pointer, else return the pointer b. When we call max, we'll pass pointers to two int variables and store the results in a pointer variable. Int star p I j. P is equal to max of the address of I and the address of j. During the call of max, the value of a or star p is an alias for I, right, which is a value. Pointer a, while pointer b is an alias for j. If I has a larger value than j, max returns the address of I. Otherwise, it returns the address of j. After the call, p points to either I or j. Although the max function returns one of the pointers passed to it as an argument, that's not the only possibility. A function could also return a pointer to an external variable or to a local variable that's been declared static. Never return a pointer to an automatic local variable. So we have a pointer is returned from this function and it doesn't take in any parameters. We declare int I in this function and we return the address of I. The variable I doesn't exist once f returns. so the pointer will be invalid. Some compilers issue a warning such as function returns address of local variable in this situation. Pointers can point to array elements, not just ordinary variables. If A is an array, then the address of A at index of I is a pointer to the element I of A. When a function has an array argument, it's sometimes useful for the function to return a pointer to one of the elements in the array. For example, the following function returns a pointer to the middle element of the array A, assuming that A has n elements. So we return an integer pointer for this function find middle, which takes an integer array A and an int n. We return the address of the array A at index n over 2. Chapter 12 explores the relationship between pointers and arrays in considerable detail. Cool. Let's just do these questions real quick. Q&A. Question: is a pointer always the same as an address? Usually, but not always. Consider a computer whose main memory is divided into words rather than bytes. A word might contain 36 bits, 60 bits, or some other number of bits. If we assume 36-bit words, memory will have the following appearance. When memory is divided into words, each word has an address. An integer usually occupies one word, so a pointer to an integer usually occupies one word, so a pointer to an integer can just be an address. However, a word can store more than one character. For example, a 36-bit word might store 6-bit characters, or 4 9-bit characters. For this reason, a pointer to a character may need to be stored in a different form than other pointers. A pointer to a character might consist of an address, the word in which the character is stored, plus a small integer, the position of the character within the word. On some computers, pointers may be offsets rather than complete addresses. For example, CPUs in the Intel x86 family, used in many personal computers, can execute programs in several modes. The oldest of these, which dates back to the 8086 processor in 1978, is called real mode. In this mode, addresses are sometimes represented by a single 16-bit number, an offset, and sometimes by two 16-bit numbers, a segment offset pair. An offset isn't a true memory address. The CPU must combine it with a segment value stored in a special register. To support real mode, older C compilers often provide two kinds of pointers: near pointers, 16-bit offsets, and far pointers, 32-bit segment offset pairs. These compilers usually reserve the words near and far as non-standard keywords that can be used to declare pointer variables. Question: if a pointer can point to data in a program, is it possible to have a pointer point to program code? Yes, we'll cover pointers to functions in section 17.7. It seems to me that there's an inconsistency between the declaration int star p equals to the address of I and the statement p equals to the address of I. Why isn't p preceded with a star symbol in the statement as it is in the declaration? Answer: the source of the confusion is the fact that the star symbol can have different meanings in C, depending on the context in which it's used. In this declaration, int star p equals to the address of I, the symbol is not the indirection operator. Instead, it helps to specify the type of p, informing the compiler that p is a pointer to an int. When it appears in a statement, however, the star symbol performs indirection. When used as a unary operator, the statement star p equals to the address of I is wrong. It would be wrong because it assigns the address of I to the object p points to, not p itself. Question: is there some way to print the address of a variable? Any pointer, including the address of a variable, can be displayed by calling the printf function using the %p as the conversion specification. Question: the following declaration is confusing. Void f const int star p. Does this say that the function f can't modify p? No. It says that the function f can't change the integer that p points to. It doesn't prevent f from changing p itself. Void f const int star p declares an integer j. Star p equals to 0 is wrong. You can't assign the value of the pointer p to 0 because it's a constant pointer. We can, however, assign p to a different address. Since arguments are passed by value, assigning p to a new value by making it point somewhere else won't have any effect outside the function. Question: when declaring a parameter of a pointer type, is it legal to put the word const in front of the parameter's name, as in the following example, where we have void function f, which has a parameter of an int star const p? Yes, although the effect isn't the same as if const precedes p's type. We saw in section 11.4 that putting const before p's type protects the object that p points to. Putting const after p's type protects p itself. So void function int star const p, if we declare an integer variable j, if we say the value at the pointer p is equal to 0, that's legal. We can change the value of which the address p contains. But we cannot change, however, the address of p, because const is applied to the pointer p, not to the value at p. This feature isn't used very often since p is merely a copy of another pointer, the argument when the function is called. There's rarely any reason to protect it. And even greater rarity is the need to protect both p and the object it points to, which can be done by putting const before both and after p's type. So we have void function f, which takes in cont int star const p, right? Where we have int j here. If we decide to assign the value of p equals to 0, that's wrong because it's const for the actual value, the integer that it points to. And we cannot assign a new address to p because const p. And that'll take us to the exercises. Cool. So I do have a little bit of notes to kind of catch up on. I'll kind of do those off stream, I guess. But you can access these notes in my Discord and also on my GitHub repo, link down below. So make sure you guys check those out. You can access these notes in my GitHub repo, link down below, and also in my Discord, which is a complete roadmap of my entire learning journey and teaching myself computer science and programming from the ground up. All right, you guys, this was chapter 11, Pointers, a complete read aloud from the book C Programming, A Modern Approach, 2nd edition by K.N. King. I really appreciate you guys being here and hanging out with me today. This was an awesome read. I really got a good kind of introductory refresher onto pointers from back when we got first exposure in CS50X. I really appreciate you guys being here and joining me. Lots of great questions and support in the chat today. We got some more to learn in the next coming chapters regarding pointers and memory management in C, so make sure you join for later streams. But I will be chopping up this stream and uploading it to the channel as a full audiobook, kind of quick, sequential, with no gaps or any ums or anything like that. So thanks so much for being here and joining me. I appreciate you guys so much. Like the stream if you enjoyed, and I'll see you guys tomorrow, where we'll continue on with probably our project or maybe take a stab at these exercises. All right, thank you guys for being here. I'll stop the recording. And then we'll go ahead and stop the stream here. All right, peace out, John.